Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, I'm going to sum up beam design from beginning to end. We've already had videos on each of the different beam design parts, including moment resistance, shear resistance, bearing resistance, deflection. And in this video, what I'm going to do is just sum them all up so that everything's in one place, and all the different clauses that you need in order to design all of these different things are all together. All right, so there's 5 different steps. The first one is load combination. The rest of the 4 are the ones that we've talked about previously: bending, shear, bearing, and deflection. So first let's talk about the load combinations. Okay, so the first step is to find all of the load combinations for all of the different cases, for all of the different types of load effects, including, of course, moment, factored moment, factored shear, potentially total load if required to calculate the shear resistance. That's the detailed shear method that we talked about, and the load for bearing. And we require that for bearing, we have 2 different potential loads that we need to compare against. One is the total load at the bearing surface, and the other is what I have been calling the squeezing load, the load that goes directly from the top of the beam to the bottom of the beam. And for each of these, I need to find one value for each KD that I have in my problem. Okay, and then on top of all those, I also need to find the loads that are associated with serviceability. So then once I have all of those load combination factored load results for ultimate limit states and serviceability limit states, then I can go ahead and start checking my resistances against those loads. So the first one that I'll talk about, and again, doesn't matter really which order you do these, sometimes maybe it's going to be clear that one of these is going to tend to govern in your problem. And so if you're doing a design and you're trying to pick different beams, and you know, for example, that this beam is particularly sensitive to shear, like it's going to be close to the shear resistance, then maybe I'm going to design check beams and then check them against the shear until I get one of those that governs. And then after that, go ahead and check all the others, the ones that aren't going to be so critical. And of course, that's going to depend on what kind of beam that you're designing. So it's hard to say which one of these, which order of doing these is going to make sense. But in any case, you're going to have to do all of them at one point or another. So I'm just going to start with moment resistance. So for each of these, I'm going to show all of the things that we need to calculate for both lumber and glulam. Often there is overlap between the two, and I'll show when that's the case as well. The other case is when it's a bit easier. So when I'm checking for moment resistance, I have 2 slightly different approaches for lumber and glulam. For lumber, I just check MR, and for glulam, I have an MR1 check and an MR2 check. One of them which considers lateral stability and one of them which considers size effect. Okay, and there are the relevant clauses, 6.5.4 and 6.5.3 for 08614 and 19 for the MR check, and then MR1 and MR2 are both in the same clause, 7.5.6.5, which is the same for both 08614 and the newer version 08619. For those MRs, often we need to do a KL. For the for lumber, we have a KL check where you'll recall we see if we have our dimensions and our aspect ratio and our boundary conditions for lateral stability. If they fit a certain set of criteria, then we can say that KL equals 1, and that's what's found in 6.5.4.2 and 6.5.3.2. But then recall as well that if I don't fit those criteria and KL does not equal 1, then I use the glulam method to check for KL instead, which is clause 7.5.6.4 for both 08614 and 08619. On the glulam side, my KL check is only that same clause. And that is basically it for moment resistance check. So pretty straightforward. Okay, moving on to shear resistance. I have a number of different things that I need to check for shear, including my longitudinal shear resistance and my notch shear resistance. And so this is going to be a little bit complicated, but we're going to map it all out, all in one place for lumber and for glulam. Okay, so for lumber, the overall shear clause is 6.5.5 or 6.5.4. And in glulam, for both versions, it's 7.5.7. Okay, so starting with longitudinal shear. Okay, so for the first bit, which is the longitudinal shear, on the lumber side, we just have one equation for longitudinal shear where the resistance is greater than or equal to VF at D. And you remember that this resistance includes a net area reduction. And when I say that it's greater than VF at D, what it really means and what it says in the standards is I don't have to consider shear loads that are within D. Now, for many cases, the shear increases as it goes towards the support. So that means that, you know, VF at D is likely the largest one. But if the VF is greater somewhere else within the beam, that is the VF that I'll check VR against. It just means that for the shear that's within D, I don't have to check it. On the longitudinal shear for the glulam side, I have two different options for checking my shear resistance. One is for smaller beams with a volume less than 2.0 meters cubed. I can use, and for members that aren't beams, like for beam columns, for example. Then I can use the simplified method, which is very similar to the method that's used for lumber, where I also, again, don't have to check within D of the support. And then for any beams, and usually I'll get a benefit for doing this, I can use the detailed method, where I check actually the total load resistance versus the total load on the beam. You remember that the shape of the load is accounted for using the shear load coefficient CV. And so if I have something that kind of just barely meets the simplified method, or it's not quite meeting the simplified method, then I can get actually usually a larger resistance by using the detailed method. And that's it for longitudinal shear. So what about notch shear? We have two different notch shear approaches depending on whether you're talking about a notch that's on a tension side of a beam or a notch that's on the compression side of a beam. So the tension fracture shear approach for glulam and lumber is very similar. There are the clauses for each. Those clauses look very similar. And what I'm calculating is an FR, which is a fracture shear strength. And I compare it to the maximum shear within that notch. So very straightforward. Then we have compression side notches. Okay, so for compression side notches, on the lumber timber side, this compression side notches are already taken into account through the application of AN in the longitudinal shear equation. So up here in longitudinal shear, the resistance includes the net area. You may recall that in the simplified method for glulam beams, there is no AN reduction. They use AG in this equation instead, which is the only difference between those two, the glulam and the lumber approach. But since that equation uses the gross area, we need to have a separate way to consider if there is a net area reduction because of a compression side notch. And so that's what these clauses do. 7.5.7.3 in the 2014 version and 7.5.7.4 in the 19 version. And these clauses are, again, all of these clauses between the two standards are basically identical, except this one has a small difference where in one there is a demarcation line on the length of the notch EC, and in 1 that limit, in 14 that limit is D, and in 19 that limit is D minus DN. So just very slightly different. Okay, so that's the approach for shear. Those are all the different things that we can check for shear. If I don't have notches, then I don't have to check these notch equations, obviously, and I'm left only with the longitudinal shear checks. Okay, so let's move on to bearing resistance. Okay, so this bearing resistance check for a beam, I need to do it everywhere where there's an applied load or where there is a support, which is also an applied load. It's just a reaction load. And the clauses for that are as follows. Okay, so the approach is identical between lumber and glulam. And basically I have two different criteria. One is for effect of all applied loads, as we've talked about, and one is our QR prime, which is effect of loads applied near a support. Okay, so I'm going to check QR greater than QF. That's my effect of all applied loads at every single bearing location wherever I have a load or reaction. And I'm going to check QR prime, the effect of loads applied near a support resistance, against those loads that are transferred directly from the top to the bottom of the beam, i.e. not transferred in shear to the reaction. And I'm going to check that at any locations where I have loads on either side of the beam that are within D, that is the depth of the beam, from each other. That's D. Okay, and then I also have bearing resistance check if I have loads at an angle to grain, which we talked about. So for loads at an angle to grain, we have a clause 6.5.8, which is also 6.5.7 in 08619. And for glulam, we have the exact same approach. In fact, the standard references just back to those lumber clauses instead of providing any alternative approach here. And for that, we calculate an NR, which is a resistance at the angle to grain, and we make sure that that is greater than NF, which is the force applied at an angle to grain. Okay, the very last check that we need to do is for deflection. Okay, so the deflection limitations are provided in 5.4.1 to 5.4.3 in both versions. That provides the L over 180, which is the primary resistance against total load. That's the deflection limitation against total load. And calculating the deflections is not specific to wood, so you can use any method you like to calculate the actual deflections of the members, but there is some help in the Wood Design Manual, pages 927 to 944, which provide a lot of tables and easy calculation methods in order to determine deflection, which you can compare against that deflection limitation. So those are all the checks that we need to do for wood. So this video summarized all of the different places that you need to go to calculate deflections, and how to calculate bending moment resistance, shear resistance, bearing resistance, and what things you need to consider when you calculate load combinations for beams. And this summarizes beams. Next thing we have to talk about is how we combine axial loads and moments together. So those are beam columns. And it's basically one extra check that we need to add on to all of these other things that we've learned so far.